general meeting of the Fort Worth Astronomical Society and my emancipation meeting. So I'm happy to report we have a quorum for the election. So we'll go ahead and get started. So again, welcome. Do we have any visitors today? Okay, then board members, if you'd raise your hand for those that are present. So I'm Bob Sirkis. I'm your current president for another 12 days. Bruce Campbell is a director. Ted Smith is a director. And where did John? Oh, John Germini is treasurer for another 12 days. He's already planning the meeting to get rid of the cards. Cy Simonson's a director. He's online. And I think that's all of the officers. Monica is not here today. Bill Hall, there he is. Bill Hall is the master of the presentation, so except for he's fighting with the projector. Okay, so I will continue on. Now I need the projector. And there's Chris Malicki, who's the director, who's been trying for 2 years to get me to stand on this spot. And I may stay here for about 5 minutes. So it doesn't look like it's on. Okay, while they're getting this equipment squared away, I want to just say a couple of things. I want to thank everybody here, all the membership, for the privilege of being the president of this club. It's a wonderful organization. I've enjoyed all the challenges, but I'm not going to miss them. And it's been a great pleasure. The three things that are important to me that we've all done incredibly well. Membership at the beginning of the year is 160 or so. This year, around 160 last year, and it was 120 or 130 the year before. But the numbers are outstanding, and it's because of the work that we all do. It's great. The outreach is really, really outstanding. It's important to me. Patrick and John, I know I saw John McCrae do really outstanding work. I'm excited with the new partnership we now have with Cook Children's Hospital. We're going to start up the indoor star parties in September when it's a little cooler and a little darker. And the partnership we have with 1687. We're going to do a presentation with them in July. So now that the equipment's back up, I'm going to segue back. Are there any new members present? Okay, so our new members, Danny, if you want to vote, you need to sign in, buddy. Chester Woodley, Robert LaHaye and family, James Swiger and family, Julie Tigner, a student. We love students. Okay. TJ Harden and family, Andy Davidson and family, and John Prindle. And John, didn't you say quite a few of these folks signed up in the last week or so? So, yeah. So this is tremendous. This has to do with all the work that we do as a group and the outreach. So, hey, this is great. Next slide. Okay. Hopefully everybody knows everything about us. Founded in 1949. As of June 1, we had, or just before the cutoff, we had about 370 members. That's the number of people that when you include families and individual memberships. We have a huge range of experience, and we're all willing to help. So if you got a question, ask it. And we're nonprofit. We love donations. And we'll give you a letter for the IRS. So we appreciate donations. Next slide, please. That's where we are, fortworthastro.com. Soon, rsoa.fortworthastro.com. I'll get into that in a minute. Facebook, YouTube, our IO groups. We have a very strong astrophotography group. Next, please. The current board for 12 more days. Myself as president, Bill Hall's vice president, John Giarmini's treasurer for 12 more days, Monica Merritt's current secretary. She's with family and helping her family out. Jim Potts is a director. He's in Africa at the moment. Ted Smith, who was over here. Cy Simonson, again, he's a director, and he's also our legal beagle. And Bruce Campbell. Yes, John? Do we have a secretary present? Yes, we do. In the present and potentially in the future. Well, we have to have that. Yeah. Okay. Next slide, please. Key contacts. Development committee, I suspect, will probably kick up again in the fall. Michelle Thiessen is the leader of that group. Tom Roth, Robin Pond, Jim McCatherine, who is online, he's our architect. So if you don't like what I'm going to show you in a little bit, complain to him. Bruce Campbell, and then outreach is Patrick McMahon. John McCrae does Tandy. Cy does young astronomers, and I will be helping with 1687 and Cook Children's. Tom Roth is our chief carpenter and Palo Pinto Mountain State Park rep. The Thompson Observatory in Keene, Texas, if you haven't been, you should go visit. It's a great place. We can go there anytime we want. We can go image and view the stars. It's Bortle 4. They have a 10-inch TMB and an observatory. It's a great place. George Lutch is our prime focus editor. Bill Hall takes care of putting the meetings together. And membership and donations is John Giarmini in the back. Next, please. Okay. Let's see here. Dr. Oliver, we appreciate you waiting a few minutes so we can take care of this important piece of business. So we have a slate of folks who are willing to run for these positions. Is there anybody here that wants to run for director or any other office? Okay, so I'm just going to ask folks to stand up. So Bruce Campbell, please stand up, is running for president. Bill Hall is standing for vice president again. Constantine Bekintis is not here. He's out of town this week, but he's volunteered to take a very important job. Treasurer. Robin Pond has volunteered to be secretary. And then Stephen Kennedy, who's online, has volunteered to be a director. And Tom Roth volunteered to be a director. And then the remaining directors until the end of 25, Jim Potts, who's in Africa, and Cy Simonson, who's online. So I make a motion. We vote by acclamation for the slate of officers. It's been seconded. All in favor? Aye. Congratulations and commiserations. So well done. Thank you. Okay, now Bill is going to introduce our featured speaker tonight.
So we've got Dr. Will Oldroyd. Oh, he has more to say.
I'm sorry, I missed, got so excited. Can you bring up my slide deck?
A whole slideshow.
Yeah. So I'm just going to walk through Rising Star. I'm going to kill the lights. Many of you may remember this look, but about 2 years ago, we purchased our dark site out in Eastland County, 4.5 acres. So I've got 11 slides, 8 of them are pictures. So this is the beginning, and this is what our entrance looked like. Next slide. And that's what it looks like today. If you haven't been out there, you're driving down the county road, that's the entrance. Next slide, please. This is the field probably the day we purchased it, so just notice, just have a look at this. And there are a lot of people who have done a lot of work, and there are too many to mention. So next slide, please. So this is our storage area and composting lavatory. Next slide, please. And electric power for that building. Next slide, please. This is the new astronomy and education building that was delivered about Saturday a week ago. It's 40, it's a high, I want to say high boy, but that's not the right term. High cube container, 40 foot long, 8 feet wide, 9 feet tall. The interior dimensions are just a tad shorter than that, but it has 2 bunk rooms that will convert into office and meeting space and 1,500 cubic foot of storage. Next slide, please. Tom Roth and Charles Haggard, 16 feet by 10 foot deck, ADA compliant ramp. I know this looks a little messy, but that's going to come off tomorrow. That's just there to make sure folks didn't step on the concrete. So that's just phenomenal. You'll notice that the 2 doors to the bunk areas will open out. It's going to be a great, just sit down and chill when we're out there. Next slide, please. Yes, Tom. Awesome. Okay, now this field, this is Bruce's crew, keeping it groomed and neat, but this is what our observing area looks like today. Okay, we have the Noble Observatory, which is the first one, another observatory that's going up, 5 lease pads, I'll explain them in a second, 5 public pads. All the pads have power, the lease pads have internet. But it looks awesome. What you can't see from Peter's scope, blocking the 20-foot maintenance building that's back there. So we're going to be self-sufficient. Next slide, please. Okay, I'm going to go through these really quick. Rising Star Observing Area features Bortle 2, and we mean Bortle 2. Okay? Plenty of on-site storage, so our equipment that's in Burleson will be on site by August the 1st. Okay? There's plenty of storage in the maintenance building, the composting lab and storage building. Our astronomy and education building again has 2 8x8 bunk rooms. They'll be separated by double doors, and that can convert by 8x16 meeting space. We'll have almost 1,500 cubic feet of storage. That's a lot of storage, okay? The 16 by 10 foot deck and ramp, that's really cool. I couldn't find a single beer, so I could enjoy that Saturday night. The smallest beer you can buy is 32 ounces. I can barely drink a pint. So we have electricity right now, internet tomorrow, literally, tomorrow morning, 8 o'clock. Next slide, please. So what do we have? Again, we have Noble Observatory. It'll be RASA 8 based, remote EAA enabled. Second observatory, which is leased by Jim McCatherine. 5 8x10 leased pads, which have power and internet. Yes? It's a telescope. It's a RASA. Okay? And then 5 8x8 public pads with power and Wi-Fi starting tomorrow. So if you need to call 911, you'll be able to. Next slide, please. Ribbon cutting. Okay, we've been talking about this for a while. Our ribbon cutting is going to be Saturday the 29th. It's a good moon for us. It's a waning crescent. It rises at 2:12. Chris Malicki is going to do our first electronic assisted astronomy live streaming. We're going to have special guests. The Cross Plains Chamber of Commerce is going to welcome the club at the ribbon cutting. The Eastern County Sheriff's Department will be there because we're going to do Star Party for them. For those that don't know, they drive by the observing area 3 times a day, 7 days a week. That's the least we can do. And hopefully we'll have some local school officials from Cisco, Cross Plains, and Rising Star. I know the school in Cross Plains has been talking us up a lot because kids have been coming up and asking. And come on and come all. I believe with the improvements that we've all put out there, and once everybody sees what we have and how things operate, you'll want to go. So again, this is something we've all been working for, and I congratulate the club for making it happen. Any questions?
What time does the open house thing actually start?
I'm not sure yet. We'll know in the next day or two. It's because it doesn't get dark till late and all that kind of stuff. So.
Because I missed it last year, but are we going to have like a little cookout? Or
Let's talk about that after the main presentation. Yeah, because that's something we need to do talk about. So, yeah. Okay, congratulations, guys.
I'm thinking about bringing a meat smoker, if that's encouraging for your attendance. Okay, so I would like to introduce Dr. Will Oldroyd. He's a postdoctoral researcher in astronomy and planetary science at Northern Arizona University. His studies include trans-Neptunian objects and involvement in the search for Planet X, asteroids with comet-like tails, involvement in a program that involves citizen science, and he's even got an asteroid named after him. But most importantly, and what's relevant tonight, is that he's involved with the DART program, and he can tell you all about that, so please welcome Dr. Oldroyd.
Thank you. I'm going to share my screen here. You can enable that. Says the host is disabled participant screen share. How's everybody doing today?
Good, good.
Okay, let's start. Okay. Here we go. Okay. Great. Today to have everyone here. Let me see if I can get the Zoom and my slideshow at the same time so I can see people. Okay, that's great. Now I can see people and my slides. So I am really excited to be here. I'm sorry I couldn't be there in person, but it seems like we have a really great group here, and this is a really cool mission that I want to talk about. So I'm part of NASA's DART mission. DART stands for Double Asteroid Redirection Test, and we'll get into that in a little bit. This was a test. There's no known asteroid threat to Earth, but we did it for the dinosaurs. Make sure that we are gonna fight back. Before I get into talking about the DART mission, I'll tell you a little bit about me. So this is me and my cute family here. Enjoy being outside and going to sporting events and disc golf. Family, making my kids play Monopoly and some other board games. And then I love going to large telescopes and observing. Here, can everybody see my mouse? I just want to make sure that I'm not.
Yes.
Yes, you can. Okay. I can barely hear you if you're in the room without the microphone, so I might not catch if you make any comments unless you have the microphone. Just a heads up. So here is me on top of the Vatican Advanced Technology Telescope, which I'm at down in Arizona. In the middle of winter, with one of my colleagues, they had to go up onto the roof to de-ice the dome. It's a 1.8 meter, and so we had these long poles, knocking the ice off, so we could look out in the observing. And here you can see in the background is the Large Binocular Telescope. And on the left here, this is me at the Large Binocular Telescope. This is one of the twin 8.4 meter mirrors. Like, you couldn't stand back far enough to get the whole telescope in the picture because it was like giant of a telescope. It's the largest optical telescope in the world, and I live really close to it. It's great to be able to use that for all kinds of research. Other research I do, other than working on the DART mission, one of the main people working on the Active Asteroids project. We have just over 10,000 volunteers that are classifying images of asteroids for us, looking for comet tails on these asteroids. And we've had over 20 discoveries in the past couple years so far, and they're still cranking out. We've had a paper come out just last month, and another one a couple months before that. So we're making lots of discoveries with this program, and I'll talk about it a little bit at the end because it connects with us. In connection with the DART mission, I've gotten to use the James Webb Space Telescope. That's been really cool. I did a large part of my PhD dissertation on the orbital dynamics of planet X and how it affects other objects out there, way on the outskirts of our solar system. And planet X, there's more and more evidence that it's probably there. We've been looking for it for about 10 years now in scanning planets, so we're still looking, but we're narrowing down where it could be. Here's another picture of a Large Binocular Telescope here to get to use sometimes, along with half a dozen or more other large telescopes around the world in space. Then this on the right here, I recently started a position with a space company called Catalyst Space Technologies, and we're a satellite upgrade company. So we build a module here on Earth, launch it in space, and attach it to a satellite to give it increased capabilities. happy to talk about that some other time. But for right now, we're going to jump into DART. First, this is what it usually looks like when I'm working as a this is what I do most of the day, is type at a computer. But I do get to go to cool telescopes and present also today. So, the big question for DART is what if, right? Hollywood has done a really good job with asking the what if question and putting it out there to put it at the forefront of people's minds. And it's not really something that people want to have happen to them. It wouldn't be the first time that it did, though. The dinosaurs had this happen. They went extinct largely. Let me jump ahead a couple of slides here. Okay, so largely this is the dinosaurs impact event right here. Right there off the coast of the Yucatan Peninsula in Mexico is where the crater from this impact event that caused the extinction of the dinosaurs was. And there were other factors that also played in, but this was one of the predominant factors that caused the extinction. It's massive impact there. Caused this gigantic crater that's mostly buried, but there's still some evidence that shows it's there. Yeah. Another good example is 2024 BX1. This asteroid was discovered in January this year, I believe the 21st of January, and it was discovered hours before it was going to hit the Earth. So it came in as a fireball in a few hours after discovery. This is an all-sky cam somewhere in Germany. From maybe the UK. And so you see that short little fireball came in and was tracked. It was discovered in space. Its orbit was tracked and calculated as it was coming towards the Earth. And then these all-sky cameras were able to capture its trajectory through the atmosphere. And that was mapped onto the surface of the Earth. Then go to the next slide here. Here, okay, so that was mapped onto the surface of the Earth. Let's go back here. And in this region here in Germany. And only a few days later, after a few days of searching, this group of people were able to find fragments of this asteroid that we discovered. This is the 8th time within the last 5 or so years, because before that we didn't have the capability. But the 8th time that we have discovered an asteroid in space, calculated that it would hit the Earth, tracked it through the atmosphere, mapped it onto the surface of the Earth, and gone and picked up the pieces of that asteroid. And that is incredible for science. These are all small asteroids, no major damage, not even a sizable crater of any kind, but all just small fragments that we've done and been able to pick up. And that is the majority of the types of asteroids that we discovered for the year. So craters are one of the most interesting pieces of the impact story. They tell the story of that. This is a picture of Meteor Crater, a Barringer crater. It's in Arizona, only about an hour away from Flagstaff, which is where Northern Arizona University is, which is where I did my doctoral studies as well as my postdoctoral research. And this crater it's a little under a mile wide. It almost hit the asteroid that impacted almost hit the visitor center right here. It came really close, but they just skimmed by. Not quite. So it happened roughly a few thousand years ago. And it was an iron meteorite. It came in and impacted and exploded just before it hit the ground, causing this large crater and pieces of meteorite fragments of have been strewn all around this area, and there was a large chunk of nickel iron meteorite material. There's a large piece of it in the visitor center and also in the, let's see, New York Museum of Natural History has a large chunk of it as well. That's very, very impressive site. I highly recommend it to visit if you're ever in Arizona. It's right there on the way to the Grand Canyon, only a couple of hours away. Definitely worth the trip there. So, oh, here are some of the stats. So, almost a mile wide, 560 feet deep. The impactor was a mere 160 feet. So this is a large asteroid, about 50 meters. This is on the scale of a Boeing 737. Okay, so the standard plane that a lot of people take, 50,000 meters. It was off by only one order of magnitude, so that's pretty good. See, so let's go. I'm going to exit this, and we are going to look at this fun asteroid launcher. So this is just a fun app I found online where the idea is you can click anywhere on Earth on maps and simulate an asteroid impact. So if we were to pick somewhere like the location of crater here in Arizona, let me get to it.
Hey, Will?
Yes.
Hey, don't mean to interrupt, but I was wondering if there was a way to maybe do something with your microphone.
Is it very quiet?
It's a little muddy.
Okay. Is this better?
I don't know.
Is that better at all? Can you hear me any better? Let me try. If we check this, can you hear me better this way?
That is a big improvement, yes.
Okay, let's go with that.
Awesome. Thank you, Will.
Didn't do very rigorous tech testing at the start. Yeah, probably should have done a little better with that, but I'm glad you can hear me better.
Yeah. Do you have the means to turn the bass down on your microphone, or is that a thing?
Bass down. I don't know on that one. Let me see. That might be a speaker part on your end.
Yeah, we've tried it. Well, at any rate, we can hear you better, whatever you did.
Okay.
Thank you.
Microphone. Let me check just real quick because I have the settings pulled up here. I can see. I don't see anywhere to change the settings for bass. I can talk in a higher voice. Maybe not. Okay. Well, we'll go with that and see if that helps. So we are zooming in on the meteor crater here. There it is. You can see it right there. So this is meteor crater just off the highway. And we are going to simulate an asteroid impact here. So this is a small asteroid. And we're going to throw an iron asteroid right there at the Earth and launch it and see what happens. This is something I really love to do with students a lot because they get a huge kick out of this. So an asteroid impact right there would have an air burst about 1.6 miles above the ground, explosion equivalent to about 8 megatons of TNT. Pretty sizable explosion. We get one of these every few hundred years on average. Most of them are going to explode higher up in the atmosphere or hit the oceans. So we don't get that many craters, but every few hundred years we get something roughly this size. Here's a nearly mile-wide fireball in the middle there, because this is where the fireball actually is. And then this is the rest of the area around it. Causes some major destruction, lots of people injured, most of them at the visitor center. Large shock wave, blowing down trees for miles. over 1,000-mile-per-hour wind speeds from this type of impact. And let's see, that's 8 miles of trees knocked in. So we can play around with this more. If you want to look at it more, I'll let you go do that on your own time. But you can simulate a giant asteroid, make it as big as you want, and destroy the entire U.S. here. You can get craters the size of Arizona, almost the size of Texas. Huge wind speeds. Yeah. Massive earthquakes. Yeah. So it's a fun toy that I found to play around with that shows kind of the destructive power of these asteroids. Okay, so now we're going to jump back in to the presentation here. Okay. There is our crater. This is a map of fireballs reported by the U.S. government sensor system. That's a little outdated, but it shows that there's pretty good coverage. There's no preferential place on Earth that these asteroids are impacting. The BX1, 2024 BX1 came in right about here. And this red point here was the Chelyabinsk event that was in Russia in 2011, I believe. Or not too long ago. It was several kilotons of TNT worth of explosion, and it exploded higher up in the atmosphere, and it was a good thing because if it had come down more, it would cause massive destruction. As is the explosion in the air, blew out windows, caused lots of injuries, but I don't believe anyone died from this explosion. And so that's normally what we're looking at on roughly 30-year time scales, 30, 40-year time scales. We get some spread like this, where there are lots of very small impacts and maybe one or two larger impacts. If you go and look at the every couple hundred years type time scale, you get something like the Tunguska event. And this one also happened in Russia, and that's just a coincidence. Russia doesn't have a preferential attraction to large meteorites. It's just really big. And so you get a higher fraction of impacts there. So the Tunguska event was in 1908. It's the largest one that we have a picture of. So this is just miles of forest, trees blown over by the airburst from the explosion of this meteoroid coming in. And it exploded in the atmosphere. The upper limit on what they estimate the explosion would have been roughly 30 megatons of TNT. So this Chelyabinsk here was like 3 kilotons. So we're talking 1,000 times bigger than that. It's pretty massive. And this particular event was on the order of the same size as the Barringer crater, meteor crater there in Arizona. Maybe a little bit bigger, but higher up in the atmosphere when it exploded, so it didn't make as big of a crater. I should include a picture of the crater in here, but I don't. But they found the crater. It's just this clearing, basically. That's what it looks like. So there are lots of these impacts that happen all the time. That's the takeaway. And so it's very important to think about how can we stop them. If we can discover an asteroid in space, measure and calculate that it's going to come hit us, if it's a big one that's going to cause damage, we want to be able to do something about it. And so the first way we can do something about that is find more of them. If we don't find the asteroids, we can't do anything to stop them. And so there are a few main ways that we find asteroids in space. The main way right now is survey telescopes. These are the Pan-STARRS telescopes, twin 1.8 meter telescopes on Mauna Kea, I believe, in Hawaii. Maybe it's Mauna Loa, I don't remember which one. Anyway, these telescopes survey the sky rather rapidly, and they're able to discover lots and lots of new asteroids all the time. I get emails every day of new asteroids that have been discovered, and a decent chunk of them come from either the Pan-STARRS survey or the Atlas survey, which is more a little more global. They have a few more telescopes spread out more across the land. And there's other surveys that discover them as well. But these are two of the main ones. And so it's just looking for them. This is an animation of all of the asteroids that are orbiting near the Earth. So here we've got the Sun in the middle, orbit of Mercury, Venus, and Earth. There's Mars, and then Jupiter and Saturn are further out. So all of the asteroids on here are represented as points. And they're all scaled up so that you can see them, because when you go out to this big of a scale, you wouldn't be able to see any of the individual asteroids. So they're all scaled up, but there's a lot of them. We've discovered roughly 1.4 million asteroids to date. That's incredible. We expect in the next 10 years to discover another 10 million asteroids, mostly through a survey called the Legacy Survey of Space and Time that'll be done on a telescope they're building down in Chile. You may have heard they just delivered the camera, which is the largest camera ever built. They just delivered it there. I might have a picture of it. It's pretty cool. All right, so this is what comes to mind when you see that type of animation, is flying through an asteroid field like this. And that's not really what it's like. You might get an asteroid field like this if it's really close after two asteroids collide. You might be able to be close up and see fragments floating around like this. But for the most part, if you are out in space on an asteroid, next to an asteroid, and you look in any direction, you're not going to be able to see another asteroid without a decent telescope. And so they're very far away, even though there are so many of them that it floods our visualizations. But here, this is an image of the Vera C. Rubin Observatory, which is going to do the Legacy Survey of Space and Time once it's finished being built. The dome has been completed. The mount is in there. This is an older picture. The telescope is almost ready to go. The camera's there. They're really close. I think next year or sometime is when they're going to be actually taking data. And this is an 8.2 meter telescope. It's the fastest telescope I've ever seen as far as slewing. You're moving this gigantic mount around very quickly. And the field of view is several degrees, which is enormous for a large telescope like this. And being with that combination, along with the largest camera ever built, it's phenomenal, a wonder of engineering the camera is. That combination is going to allow a survey of the entire sky visible from this excellent site in Chile every 3 nights, which is insane that you can survey everything that fast over and over and over again for 10 years is the survey plan. And with that, that's how we're going to discover 10 million new asteroids. That's how we're going to discover thousands of more comets, probably more interstellar objects or objects coming from other stars. And near-Earth asteroids are one of the primary focuses that people are really looking at with this, is to try to find as many of those as possible, because we want to know if there are large asteroids out there that are going to hit. As of right now, none of the known asteroids are on collision courses with Earth, but there's lots more to find. So we're looking forward to finding more. One other thing about LSST is that the amount of data it's going to collect is going to be on the order of petabytes every night, more than a petabyte every night, which is incredibly huge for the amount of data. And we're going to discover things out to 25th magnitude, which is incredibly faint. For reference, Pluto is 14th magnitude, and every 5 magnitudes is 100 times fainter. So thousands of times fainter than what you can see with normal telescopes. So this is incredible. We're looking forward to that. We want to find lots and lots more. Okay, another way we can study asteroids and find out about them to learn what kind of properties they have, which will play into them impacting us or us impacting them, are spacecraft missions. So this is a recent mission that just sort of finished up. This OSIRIS-REx. They flew this spacecraft out to an asteroid called Bennu, and they went down to the surface. This is what Bennu looks like. They went down to the surface and kind of blasted it and vacuumed up material. So they went and essentially took a chunk of material, vacuumed up a chunk of material. It's a very interesting porous surface, but they got some material and then they brought it back to Earth and landed it somewhere in the Utah desert. So this is a couple of scientists picking up the sample capsule and bringing it back. And it was just recently opened. So this is them, I think they're trying to open it. It was stuck in some way. It didn't work quite as expected based on the conditions of collecting the sample. But they were able to open it and look at the material. It's this very, very dark black material that happens because radiation from the sun just obliterates the surfaces of these asteroids and blasts them. It's this silicic rocky, sandy material that's actually has a lot of hydrated material in it as well. So water is on these asteroids, and that'll come into play in a little bit here because water is a key resource in space. Okay, so step 2 is find them. Step 2 is how do we actually stop an asteroid? So there are a few ways to stop an asteroid, and I made some really cheesy PowerPoint style animations to do this. My kids helped me with them, and they love this. So method 1 is destroy the asteroid, and method 2 is move the asteroid. So method 1 is you nuke the asteroid, and that has one major drawback is that if you nuke an asteroid, one, you have lots of slightly smaller asteroids on the same trajectory still going to hit Earth. So instead of one big impact, you're going to have lots of still pretty big impacts, and then they're also radioactive. So that's not a great option. People really don't like that option. Move the asteroid seems much more attractive, especially because the Earth moves 1 Earth radii every 7 minutes, roughly. And so all you have to do is change the speed of the asteroid enough that it's going to miss Earth by 7 minutes. So if you have a long lead time to do that, you can make that change much more slowly, and that's plenty to stop an impact. So that's encouraging. So our method 1, we're going to attach a whole bunch of rocket boosters onto an asteroid and fly the asteroid out of the way. That's a method that's been proposed. It would definitely work, but the logistics of getting rocket boosters attached to an asteroid, much less getting them there, is a little complicated. You need to take a lot of fuel, and fuel is very heavy, and so it's much more difficult to work with. Okay, so method 2 for moving an asteroid, we're going to take a large mass, not necessarily the Starship Enterprise, but some sort of spacecraft with a large mass. Maybe it has some other, a smaller asteroid with it, or just any way of having a large mass, and you fly it in what's called a halo orbit. So you are kind of pseudo-orbiting this asteroid and using some fuel to correct the motion, and that allows you to pull the asteroid with gravity. So if you have a large mass, you're gravitationally pulling this asteroid as you pseudo-orbit it this way. And so you're able to pull it. That one, the biggest problem with that is getting a large mass there. It's kind of the same problem as the fuel. where it's very difficult to transport a large mass, where fuel is a large mass as well. Okay, so we're going to try another method, and this method, this is one of my favorite ideas, is you take a giant paintbrush or some other way of applying paint, and you apply a very bright white paint to one side of the asteroid, not the whole asteroid, just one half of it. And because it's so black, and this side that we just painted is very white, the radiation pressure from the sun reflects off of it differently. And that produces sort of a heat. It thrusts as it emits light or emits heat preferentially differently based on the different colors. And that can over time change the orbit of an asteroid. Really cool idea, and probably a lot easier to bring a moderate amount of paint and a large amount of fuel or a large mass with you. So this way could totally work, hasn't been tested, and you'd need longer time spans to do this. But, I mean, who doesn't like tagging up some asteroids for the dinosaurs? Okay, so our most practical method that we've been able to come up with so far is the one that we actually did, and that's the one where we take our spacecraft with some small to moderate amount of mass, get it going really fast, and crash it into the asteroid. And this will change its orbit to move it on its orbit slightly. And that's what we did with the DART mission. That's what we tested, and let's see if it works. So here is a schematic diagram of the DART mission. Again, DART stands for Double Asteroid Redirection Test. And that is because we hit this asteroid right here, which is the moon of a slightly larger asteroid. And we did that because we wanted to test in a confined laboratory. We didn't want to be hitting some asteroid that was then going to have a chance to impact Earth. We want to hit the small one to change the small asteroid's orbit around the larger asteroid as a test case to show if you hit an asteroid, you can change its orbit. So that's what we did. It had sort of an animal sidekick here, like a Disney princess called Licha Cube. It was a small little CubeSat that flew along and took pictures as it went. And we were also watching from telescopes all across the Earth and in space. It's a very, very coordinated effort to observe this impact. Excellent. The mission originally launched in July 2021, and after a couple Earth gravity assists, it was going pretty quick. Here is just some scale for you. So here is our craft. The asteroid that we hit, Dimorphos, is the one that we hit, where Didymos is the larger asteroid. So here's Dimorphos. It's about the same size as the Roman Colosseum. And then our DART impactor is about the size of a large golf cart, but much heavier. It's like if you loaded up a golf cart with a bunch of heavy metal and then stuck some large wings on either side. So this stand, we're going to say, is about the right size to be hitting our asteroid, and then that's about the size of the wings on either side. And so it's going to come in and hit this asteroid. It's a sizable fraction of the asteroid because the asteroid's really small. It's on the order of, a couple hundred meters or less. Here is another roughly to scale drawing. So here's Didymos, the larger or primary asteroid next to the Eiffel Tower, and Dimorphos. They're further apart, but this is the relative size scale. And there's our golf cart coming in. So this is the scales that we're dealing with, and we're hitting it with a relatively large impactor going pretty fast to be able to hit it. The speed that we're going is like 200 times faster than you drive on the freeway. So we're really cooking. This is the video of the impact that happened September 2022. So we're almost at 2 years. But we're coming in. It has to do all of the tracking all by itself, so that's why it did a little nod to make sure that it's focused on the asteroid and not the other asteroid. But we want to hit Dimorphos here, And so it's all of this computerized tracking to get it just right. We're coming in, and as we go, this is just individual frames. And then that was the last picture we had. So we're gonna watch that again because it's so cool. Okay, so this is the video of the impact. It's sped up a few times here at the beginning, but then we'll get into closer to real speed towards the end. So coming in, it's doing all this tracking by itself. The mission team is watching, not breathing, basically, just trying to see, are we actually going to hit the asteroid? We hope all of our computer algorithms work so we don't miss. It's coming in, and there's lots of oohing and awing at this point, and then we go and hit the asteroid. Super cool. Here's the closest full frame. Oops, let me go back to here. Right here. There we go. Closest full frame image that we got right before impact. This is a large boulder here, a few meters across, and we're just gonna smack the thing really hard. After the impact, we don't think we left a crater. We think we changed the shape of the asteroid because of how hard we hit it. That's pretty awesome. This is where I got the title for the talk, For the Dinosaurs. There's a classic scene in The Lord of the Rings where Aragorn is charging in to say, we're doing this for Frodo, as like a last-ditch effort to make sure that everything will work out. And so it's for the dinosaurs. We know that they didn't make it, but we're doing this for them so that we might make it too. So when we hit it, we launched a lot of material off into space. It created these tails. Oh, okay. So I already talked about Leaching Cube a little bit. So this is an image from Leaching Cube showing a lot of the material that was lofted off of the body. Some of it landed on Didymos, the other asteroid here. And you can see there's chunks and boulders, pieces that flew off. It's incredible. Where is the animation that I have? That's what I want. Oh, we observe it on Earth using telescopes. Okay, so we used it with observed it with lots of telescopes. The animation I have is in a minute. This is the Lowell Discovery Telescope, a 4.3 meter near Flagstaff. I get to use this one all the time. It observed the impact and observed the Didymos Dimorphos system for a long time after. Just making sure everything was good. This is from I believe this one's from a telescope in South Africa. Took this time lapse where with the impact, it just shed this cloud of material that came off very quickly at impact. You just watch this over and over again. It's mesmerizing, the amount of material that's flying off of that. Along with ground-based telescopes all over the Earth observing this in tandem. Also at the same time were observations with both Hubble and the James Webb Space Telescope. And these were done simultaneous with everything else as much as possible. This was the first time that Hubble and James Webb were used together on the same target at the same time, and along with the ground-based response. I mean, this was the largest observational campaign of a single target ever. We observed it a lot. And we're still going through data, trying to figure out what it means, trying to understand it better. But here are images from Hubble, and this is from the James Webb Space Telescope. One of my main parts with the DART mission was using James Webb to observe the impact and then analyzing the data afterwards, trying to make sense of it and really pull out as much in the data analysis as possible. So I went in and tried to get rid of as much of the noise as possible so that we just see what's going on with the actual impact on the asteroid. So here are some time-lapse videos of the impact. You can really see that there's material flying off. You can see small chunks and boulders coming off in this one in particular. And that's still being studied. There were dozens of boulders that were launched off. One of my colleagues has made VR interactive video you can watch. So if you wear a VR headset, you can watch it, and in 3D you can see all the boulders fly out, and it's amazing. He's gone through a lot to tease all this information out of it. Very, very cool. This is an animated infographic. Okay, so this is what we did. This is showing how successful we are. So here's the original orbit. It's flying around there or orbiting. We're observing it from the Earth all the time and in space. Didymos is the primary. Dimorphos is the secondary asteroid. We're going to come in with DART and we're going to hit it head on like that. And the reason we do that is we want to slow it down, because when it moves slower, that will make it in a smaller orbit. So we impact and it moves onto a new orbit because it's moving slower in its orbit. We could have hit it from the other side to make it go faster, but this was the most optimal way with all of the pre-studies to figure it out. So we moved it onto a new orbit. It was incredibly successful. We changed the orbital period by 11 or 12 minutes, which is more than the 7 minutes, so wildly successful. We're very confident that if we detected an asteroid coming to Earth, that we would be able to change its orbit with an impactor like this if we have enough response time so that it doesn't hit the Earth. Absolute success. We're confident that we can get it to work. And that is the biggest takeaway from the DART mission, is that the test worked. We think it can work again. Now I'm just going to talk about a few of the additional science results that I've been focusing on. And the main one is this large tail that was there for months after the impact. So here's this one. You can see it has 2 branches, sometimes the tail. What else can we learn? Okay, why are we talking about that? One thing that I study a lot is active asteroids, or asteroids with comet-like tails. And this is a small population that's not very well understood. It's a big mystery in astronomy why these asteroids look like comets. Sometimes when they're orbiting like asteroids, but then all of a sudden they'll have a comet tail. And so we made our own, and that's a perfect case to study it. So this is an image that our team took from the Vatican Advanced Technology Telescope. That was the one I was on the roof with all the ice. And so we took this image, stacked a few of them together to get this really nice looking tail profile. And we are still studying this tail, trying to understand what makes it like it is. Is it like the other active asteroids, or is it different, and why? So that's part of this program we have called Active Asteroids. Like I said, we've got over 10,000 volunteers classifying images of asteroids. Here are some of the discoveries that we have. There's a cool AI art image of what it might look like, what an AI came up with that it would look like. But we have lots of discoveries with this, and we're finding new things all the time. And so you can join this project if you would like. You can go to activeasteroids.net and then click here to get started, and that'll take you to Zooniverse, which is a citizen science platform where you can volunteer and go and help classify data. And so you just click here to get started, and then it'll show you pictures of asteroids, and you can say, yes, I think I see a tail, or no, there's no tail. And it shows you a tutorial and talks you through some of the pieces there. And it's a really cool project. We have people who have helped with our project. We have co-authors on pretty much all of our papers through this project with that. So that's a really cool thing. And we're a very, very successful project studying asteroids with tails, just like this one that we made with the DART mission, and comparing those ones with Didymos and the system that we impacted. So that's a really cool study that we're doing. Lots of cool results. It could be its own talk. Then we use telescopes all over the world and in space to study those asteroid tails that we're finding, or comet tails on asteroids. I love pictures of the Large Binocular Telescope because it's so iconic and cool looking. And we use it for our studies, so I have lots of those. So in summary, the goal here is to protect Earth from asteroids. So we have to find them and we have to move them. Those are the two main things. And we use telescopes like Pan-STARRS and Atlas, and then we use LSST once it's online next year to find lots and lots of near-Earth asteroids, millions of them. The DART mission showed that we can change an asteroid's orbit if we have enough warning time ahead of time to be able to launch and hit the asteroid to change its orbit. 7 minutes so we can move it out of the way, enough that it will miss the Earth. And then by studying Didymos, we can learn about active asteroids in our solar system and learn about where the water is in our solar system, which is an extremely valuable resource when it comes to space exploration and everywhere. So those are my conclusions, and I'll take any questions. Thank you.
I have,
Definitely use the microphone if you have questions, because otherwise I won't be able to hear you very well.
yep. So I'm Bob Sirkis. I have a question for you. Were you guys able to estimate the amount of energy of the impact?
Yes. I don't remember off the top of my head, but Wikipedia does.
Okay.
So, look, I can pull it up right here. DART impact energy. Let's see what it says. Where is it? No, that's the power that powered the spacecraft. Let me know if you see it. Where you can find it.
My eyes aren't that good.
Okay. Observations of the impact. Let me just try to find energy on here. Because yeah, it was a lot. So, 19 gigajoules, the equivalent of 4.8 tons of TNT. So this was bigger than the Chelyabinsk impact. That wasn't an impact, but the explosion above Russia in 2011. We hit it pretty hard.
Any other questions? Lots of them.
Awesome. Is there a way that we can turn the camera so that I could see the room? Is that a possibility? If it doesn't turn that far, that's okay. Oh, awesome.
Solar glasses on.
Awesome.
Okay.
Here we go. Thanks for coming.
Okay, so I was wondering, how do we get our own asteroid named after ourselves?
So, to get an asteroid named after you, usually you need to get a PhD studying asteroids. Most people who have an asteroid named after them are asteroid scientists who are active in the field and who have made significant contributions. I think there are some other ways. If I remember right, the Beatles might have asteroids named after them. Greek mythological characters have asteroids named after them, and some other famous people. So you either need to be an asteroid scientist, that's probably the most straightforward way, or be super famous and have someone who nominates asteroids to be named like you enough to decide that it should be named after you.
Or discover one.
So there's this whole committee on the International Astronomical Union about naming things, and it's tricky to name just about anything.
So I have a question about how long it takes to put together a mission to get out there and bump one of these asteroids out of the way.
So this mission took several years. It was several years in the making, but it was the first one. If it was an emergency mission and there was essentially unlimited or a high level of funding, we could bring it together pretty quickly to be able to put all the pieces together, strap it to some rocket, the biggest one we can find, and launch it out there as fast as we can. I think if there was enough of a threat that people would come together to make it happen on that front. The main reason things take a long time is funding, actually. So you get a mission like this funded, it's pretty competitive to get mission funded. So you have several different missions that all propose at the same time, and then out of the group, they'll probably pick one out of the 10 to 30 missions after a few narrowed down steps. And so a mission like this, it has years in the planning and concept design process, and then about a year or two in actually making the spacecraft and getting the launch set up and ready, and then it can take, I think this one took 10 months. After it was launched, it took 10 months to get to the asteroid before impact.
So is that gonna save us? I mean, it's that time, that seems like a long time.
Yeah, it is a long time. And so as far as the actual spool up goes, I feel like we could get it done in under a year if everybody came together and there was funding for it and enough manpower on it. So I think that if there was a real threat to Earth, that people would really come together and make it happen. As far as getting the spacecraft there, this one was trying to conserve fuel. If that wasn't as big a mission, we could go faster. And so if you throw more resources at it, you can go a lot faster. It's just less efficient. But that's why there's such a big emphasis placed on finding these. And all of the big ones should have been found by now. So it's more of the medium-sized asteroids. So not the dinosaur killers, but the city killer sized asteroids, where it's not going to have this massive global reaching destruction, but more like very localized but high level destruction that we're most worried about. And so we're going to find 10 million more asteroids and probably find a few of those, be able to calculate their orbits very precisely to make sure none are going to hit us. And if one was going to hit us in the near future, then we'd be able to go do something about it.
So how do you keep track of 1 million asteroids so that you know when you've found a new one?
That's a great question. NASA has a database here. It's called the Small Body Database. This is an example. This one has the orbit of 2024 BX1, which is the one that we tracked, the very small asteroid that we tracked that hit earlier this year in January. And so it just shows the orbit at the same place as the Earth. But every single object we discover is recorded in this database and updated constantly and tracked through the Minor Planet Center and several other coordinated databases that all work together to make sure that we have the best data possible for every single object in space. Whether that's an asteroid, a planet, or a spacecraft, Elon Musk's car that he launched into space is tracked on there. Everything in space is tracked. Satellites, we make sure we track it all. That's a lot of people work on that night and day to make sure it's up and running all the time. Great question.
You said the orbital period was changed by 11 minutes. What was the original orbit time?
Oh, okay, let's go to this. The original orbit, I have it in here, and I should know this off the top of my head, but I'm blanking on it right now. It was a few hours, on the order of 12 hours. We're just gonna Google this. Google hours. Nope. The North Okay, so its original period, oh no, it was changed by, so the initial change, sorry, I misspoke on this. The initial change was 11 minutes, and then over time, it changed even more to be closer to 30 minutes. And so the original period was close to 12 hours, and now it's close to 11 and a half hours.
Next question is, how do we know there aren't some really small but highly dense asteroids out there which are much more difficult to target? Something, like the size of a baseball with the density of a neutron star.
So something like a primordial black hole or something very, very tiny.
Exactly, some black hole that's moving around.
That's a good question. We haven't seen any of those in the near space.
They're too small.
That we know, yeah, they're too small. The only way we'd be able to detect those is through gravitational perturbations or changes on other things. And if it was coming fast at Earth, we wouldn't have any time to react and there's nothing we could do. But since we've never seen any, people are less worried about those, whereas we know that there's millions of asteroids nearby. That's one of those things where it's hard to do anything about because we don't have a good way of finding them. And we've seen lots of asteroids hit the Earth, but we've never seen one of those hit the Earth. Because the Earth would be gone. But we've never seen one of those hit anything.
I heard of a named asteroid, Apophis, I believe, that's supposed to become like 20,000 miles from the Earth in like 5 years or something. Could come between the moon and the Earth. I would think that's pretty high on your list.
Yeah, Apophis is one of the most tracked asteroids in history because it is a relatively large, so like a solid medium to small, or smallish medium, we'll go that, hundreds of meters size asteroid that comes very close to the Earth. And for a long time, people thought it was going to hit the Earth. They did orbital simulations, and it looked like it would, because it was so close, it looked like it might hit the Earth, and so it was very, very high on everybody's radar. And then after observing it for more years, the orbit's been refined, so now it's just a very close pass. We're very, very certain it's not going to hit the Earth based on that. And it's going to be a great opportunity to study it. But it is a really, really interesting test case, and the fact that it's coming right now means that there's probably more stuff out there that's going to be on these type of close orbits. Another thing to think about is that asteroids, for the most part, just sit on their same orbit for millions of years. But there are some subgroups of asteroids that are similar to comets, and they can change their orbits every few years based on encounters with Jupiter. So it'll pass close to Jupiter, and that'll change its orbit to something else. And so that's the type of thing that we want to be worried about and find a lot more of those, as well as the ones that are really close to the Earth, because those are the ones that have the potential to sort of evolve in their orbits over time to be on potential collision courses with the Earth.
Any other questions?
Further out.
Any other questions? Okay, one more question.
So how far can you track into the future until the uncertainties sort of all combine until you reach a half a Earth diameter of uncertainty?
That's a great question, and the main factors that depends on are, one, how well we've measured the positions and velocities of the asteroid. So if we can take really good observations of a particular asteroid and be very, very precise and accurate about it, then we can get very good orbital information to track them as they move through space. And the uncertainties, I don't know on the specific value of the uncertainty when they're higher than that. but it really depends on how good the measurements are. The other thing that comes into play for those asteroids, especially the ones that come near Jupiter, so things like comets and asteroids on more extended orbits, is those ones, when they have a close encounter with Jupiter, even a tiny difference in how well we've measured it can have drastically different results on where the asteroid will end up on its orbit. For example, if an asteroid passes close to Jupiter, it could either end up on a different asteroid orbit, it could be thrown in towards the inner solar system, or it could be ejected from the solar system, all from the same asteroid. Just probabilistically, you could try to do the math to figure out, okay, maybe it's 30% going to be thrown out of the solar system and 10% going to be thrown towards the sun, and the other 40% is going to be on its orbit, but maybe it'll actually hit Jupiter. So you have to do this sort of guessing game to try to figure out what it's actually going to do. And you do that with lots of simulations and math to try to figure out, okay, this is most likely what's going to happen. And if we get better measurements, we'll know that much better, to a much higher probability.
Okay, Will, thank you so much for taking the time to speak with us. Keep up the good work to save us all. Is there a hotline for everybody that's going to have a sleepless night tonight?
Yeah, you should just go watch some of those Hollywood movies about asteroids hitting the Earth. That's
right. That's right. Desensitize, right?
Yeah, there you go.
Thank you so much, Will. Appreciate it.
Awesome. Well, thank you, everybody, and have a fantastic day. Thanks for inviting me.
And we're going to go to break. 10 minutes.
10 minutes. my favorite time, the raffle time. We're doing 5. Has everybody that's interested in participating in a raffle participated? In other words, we're happy to take your money. Oh, is everybody back? I don't know. It's impossible because people leave, actually. 480-7410. Oh my gosh. Constellation Gaff. 480-7410. Tom Nelson. All right, come on down. Four eight zero 7416. First time winners. Thank you. Pick anything here. Do what you want. Pick what you want. Yeah. Then you got it. Thank you. You're welcome. Four eight zero 7427. 480-7427. Someone said bingo? Okay.
What do I get?
Pick anything.
Oh.
It's 3. Four eight zero 7445. Didn't you win already this year, like twice? Disqualified. 480-7443. 480-7443. Did anybody win? Okay, since it's my last meeting as president, we're going to do one more, and Phil will have to run to catch me. Four eight zero 7442. Disqualified. 480-7457. We have a winner. In here? All righty. Now for the fun part. What's in the Sky, June and July 2024, Mr. Velvet Voice, Bill Hall.
So I was in California last month doing it over Zoom, and I start the slideshow, if y'all remember, and I was like, next slide, and I'm thinking to myself, man, Chris, get it together. And then I was like, oh, Bill, get it together. I had to advance my own slides. Muscle memory. All right, so this is what's in the sky for the next month before the next meeting. Bob Sirkis as our picture in the front end of the slideshow here. Go to the next slide. This is the Ophiuchi complex. Good stuff. Next slide. All right, so bright comets in the upcoming month. These are comets that are magnitude 10 or brighter. So 12P, as you can see, is out of the picture now. But 13P, Olbers, is about to take the big spotlight here. They're actually expecting, and of course expectation with comets are we'll see you when we see it. But they're talking about the potential of 13P actually getting as bright as Vega. So we'll see. We got 2023 A3 that's magnitude 9.3, and both of these guys are brightening, obviously. And of course, you see my laser. I'm not using my Hotech anymore. I wised up and just bought one. So I get my information from Aretha.net. This picture, by the way, this is my picture of the eclipse, and I had read after the eclipse that there was a comet, not 14P, because that was in the sky too, yeah, but it was going to be way out of the shot unless I had a really wide shot, that there was another comet that had just been recently discovered before the eclipse, and I read that it was really close to the sun. So I'm looking through my pictures, and I just do a nice light stretch on my picture, and I'm looking, and I'm scooching over, and it's like, oh my God, there it is. It's a comet. It's the comet. So I squealed a bit with that one. I was like, oh, I caught it. Oh my gosh. So next slide. Occultations and close approaches for y'all that like this sort of thing. It's Tuesday, June 27th. We got Moon and Saturn. There's a little over 4 minutes apart. The 28th, in the middle of the night, Moon and Neptune are about 15 minutes apart. And Saturday, July 13th, the Moon's gonna occult Spica in Virgo. Next slide. We got the full moon in June on Saturday, June 22nd, and this is Robert Cargill's one of his beautiful moon pictures. He's really into that and is pretty good at it. Next slide. So Ceres comes back around to its opposition closest to the Earth, where the Earth is between Ceres and the Sun. And it's in Sagittarius this year, and it's going to be magnitude 7.3. One of the fun facts about Ceres is that something they discovered with the Dawn mission, I think, is shiny bits on there, and they're considering it either ice or salts of some sort. But they have found that there is water on or in Ceres, and that there's actually evidence of a very thin water vapor atmosphere. So kind of a cool fun fact about our first discovered asteroid. Next slide. New moon is Friday, July 5th. Next slide. So every once in a while, maybe once a year, Maybe not always once a year, but there is what we call the double transit season. So sometimes it's just once. Rarely is it ever 3 shadows on the moon. But when you got 2 shadows on the moon, like I've got in the picture that I took in, what was that, 2021 of Ganymede and Callisto, it's really cool. You get that depth of field, and this begins on July 13th. And next slide. So for the next month, you've got one after dawn on July 13th, and just after midnight of the same 2 moons on July 16th. So this actually continues through July and August. So if you're into this sort of thing, it's a really cool thing to check out. That's what's going on Jupiter. Next slide. So the constellation I'm going to feature this month is Draco, dragon. It's a Latin draconum, which means huge serpent, and Ptolemy, just like with Cancer, Ptolemy actually featured this in his Almagest in the 2nd century. It was the first time that it had been featured in a star catalog. It's got 9 stars with known planets, lots of formally named stars. It's a really big constellation, and it's circumpolar, so it never sets. And its notable asterism is that little keystone shape set of stars that makes up his head, and oddly enough, they call it the lozenge. Next slide. So there's the lozenge, you know what I'm talking about. So the Cat's Eye Nebula. This is a planetary nebula in Draco. It's also known as Caldwell 6. It's actually one of the most complex known nebula, just because of the layers and layers of matter that's been expulsed. It's been the expulsion of matter off of the central star, and possibly a binary that's dying and releasing all this gas over all this time. Puts off about 20 trillion tons of mass per second. Next slide. This is actually Stephen Kennedy's shot of it. It's a very difficult thing to image because it's just got an incredibly broad range of brightness from its extremely bright center to extremely dim outer perimeter there. Next slide. This is actually Hubble's image of it. This is Hubble's image of that little center bright part. And you can see how complex it is. You've got the center star, possibly a binary. You've got these 3 rings, and you've got polar jets, and just layers and layers. It's beautiful planetary, but extremely complex. Next slide. So the Draconids, it's near the lozenge. It's a great meteor shower. Sometimes it's a dud. Sometimes it's quite amazing. I think in 2011 it had like 600 per hour. So it has its bursts. It has its outbursts every once in a while. 21P comet is the reason for this meteor shower. And yeah, it's a good one. I think it's in October, yeah. Next slide. All right, M102. So it's known as the Spindle Galaxy. There's a spindle galaxy in the constellation of Sextans, which is a southern constellation, but we're not talking about that one. It's got, next slide, it's got a great, really notable dust lane in the center of it. Just a beautiful constellation. Next slide. So, Draco Dwarf Galaxy. This is one of like the 2 dwarf galaxies that are found in Draco. This is yet another satellite of the Milky Way galaxy. And I always like to feature these because you don't think about how many galaxies are orbiting our galaxy. So I like to point that stuff out because it's not just as simple as this galaxy that we're in all by itself. There's all sorts of acquisitions that it's made over time. The interesting thing about really any dwarf galaxy is the distinction between the velocities within the galaxy and how those sort of measurements actually point to dwarf galaxies having a large amount of what could only be dark matter, because they haven't found anything else to explain how the galaxy holds together with that sort of thing going on in it. Next slide. Right here next to the lozenge. So, little guy here. It's very dim, but it's there. Next slide. Tadpole Galaxy. I love this galaxy. This is an ARP catalog galaxy, so it's a weird one. It's gotten beaten up a little bit. It's gotten kind of pushed around by other galaxies and stuff, but it always ends up being some beautiful devastation that results. This one is around the body of it down here. The Trail of Stars, go to the next slide here. It's a barred galaxy. This line of stars right here is about 280,000 light years long. This is almost 3 times the diameter of the Milky Way galaxy. So it's very aptly called the Tadpole Galaxy, but just a beautiful result of a multi-galaxy interaction. Next slide. And then there's the Draco triplet. So everybody knows about Stephan's quintet and the Leo triplet. Not a lot of people know about the Draco triplet. It's a line of sight grouping. These 3 galaxies are not interacting, and it's NGC 5981, 5982, and 5985. Kind of a variety of different things. And it's right here at the bend near that tadpole. And go to the next slide here. So you got a nice little mix of galaxies here. You got a near edge on, you got an elliptical, and then you've got a beautiful, almost face-on spiral. So a really cool grouping. Next slide. And that's it. So there's a list of like 354 deep sky objects. There are a few, actually there are a lot of other beautiful spiral galaxies in Draco. And I think a couple more ARP objects as well. These are my sources and stuff. But also, Draco is actually also featured in the most recent volume of the Annals of the Deep Sky, which the early volumes are things that our very own Dennis Webb was contributive to. And next slide. And keep looking up. This is John Dries. He captured the lunar X. It's a particular time where the Terminator, the lunar, the shadow Terminator on the moon, just creates a shadow over some geological features that shows an X in the shadows. So there you go. Thank you very much.
Thanks, Bill, very much. Would you go ahead and hit the lights for us?
All right.
Solar glasses, everybody. I'm going to hand it over to
Watch your eyes.
Patrick McMahon for our outreach report.
Okay, so do we have that slide up, or I don't know if we got a slide together for the next star parties? All right, so it's we're on a light schedule right now. So as I posted the other day, that's the next two star parties we have between now and the next meeting. We have one in Grapevine on Thursday. It's going to be a small group, so I don't need a lot of scopes. And then we got Cleburne State Park this Saturday. And if anything else comes up between the next meeting, I will post on the e-group. Thanks.
Thank you, Patrick. Patrick does a great job doing all these events for us. John McRae will talk to us about Tanny Hills.
Okay, I'd like to start out by thanking everybody that came out last Saturday night. It was hot, there were clouds, and it was buggy, but we had 10 scopes. 2 of them, I believe, were from non-members. One of them was a young lady from the Northwest Independent High School District. They brought a small scope out and is interested in astronomy. We had probably 20, maybe 25 to 30 guests that came out. So it was a pretty good evening after all. Our next star party is July the 13th. Sunsets at 8:38. So like to tell everybody, if you're new to the club and you're interested in what kind of telescope, come on out because we have all types. If you have a scope and you need help setting it up and running it, come on out. We'll be glad to help you.
John, you said it was July the 13th, the next Yes. Yeah, Chris, the next slide actually shows that information.
Okay, cool. I thought Matt said Friday the 13th. Okay. All right. And we're going to attempt a remote EAA on Saturday the 13th to something paired up with Tandy. So, okay. Cy, you're online, right, big guy?
Yeah, just next slide, I think, should be mine.
Yep. Young astronomers.
Yeah, I know, next one, yeah, okay, so, it's fourth Tuesday of every month, so we got one next week. We're gonna start at 7:30. The sun doesn't set till 8:40, but we're gonna give a class on galaxies, that should be interesting. And I need some people to bring telescopes. I'm still unable to lift mine because of my shoulder surgery. I'm still out for another 2 months, so I could use some scopes out there to help out. Well, it's at the Bedford YMCA. And if you have any questions, all the information is on Night Sky Network, our calendar.
Thank you, Cy. We only have one event at 1687 in July. It'll be on the 20th. Our events in June were canceled because the late sunset and the really young kids. So Saturday, July the 20th, and we'll be there at 6.
So ignore all that except the bottom line.
Yeah, okay. And Bill was trying to give me super secret code here. I couldn't get to it. Bruce or Michelle, do you have anything to report? Oh, okay. Thank you. Bruce's presentation was a duplicate of mine. Yep. Tom, for Palo Pinto?
We're still going to open up summer of 2025. Things are coming together nicely, so. No, we're still, they keep moving us. Originally, we were going to be in the darkest part. It was too much to put a road up there, like $4 million. But now they've extended that road up to somewhere where we were originally. So things are developing. They'll put us in a dark spot. So.
Thanks, Tom. George Lutz, are you online? I don't think we have any changes.
I'm here, sir.
Oh, okay. Website and media report, please, if any.
No changes.
All right, thank you. Anybody have any announcements?
I want to say something. So it has to do with you. So, you know, when we first, when you first took office, and I got into the vice president position, you and I spent a lot of time talking on the phone, talking out at the dark side. The one thing that I marveled about with this guy was, first of all, I had to continue reminding myself that this guy wasn't retired. And it was like, I just kept asking myself, I was like, where is he finding all the time to drive the things that he's doing with this club? So I just, thanks, man.
Thank you. It's a pleasure. Any other announcements?
I have one. If I may. Steve Kennedy here. On behalf of the Astrophotography Special Interest Group, we have a little gift for you, which I will present to you very soon. It is a filter for use in your telescope, your RASA. It is the IDAS Nebula Buster, and a bunch of the members all pitched in to pay for this for you. And when I see you next, we'll present you our little gift and our thank you for everything that you have done for the Astrophotography Special Interest Group. Thank you.
Thanks, everybody. Really appreciate it. I want to take a moment to give a special thanks to, this dates me to a big lug, Mr. John Giormini, for spending the last 5 years of being treasurer of this club, which probably wasn't too bad until I came along and made the last 2 years really challenging for him. He's done a hell of a job. He does more than just the treasury stuff. And we frankly wouldn't be here without his time, effort, and frankly his attention to detail. So big, huge table rumble to John, and then we'll turn it over so he can give us his final treasurer's report.
Lord. Well, that's great because my mental health insurance would be running out. All right, is it pulled up? It is pulled up. We can almost see it. Well, those numbers are not right anymore because tonight we had additional people join, as well as had to write a check for $714. So those numbers are not there. The major thing that went on last month, or during the last 30 days, I should say, is the dues to the Astrological Society, Astrological League. Yes, thank you. Astronomical League. What is it? Yes, that one. Okay, so we paid dues for the highest number of members we ever had. Right now, we're sitting at, I think it's 222 people. Unfortunately, we have 48 people that haven't renewed. So as we've discussed in prior years at this time, we're reaching the cliff. And so that cliff is going to be in the mid to upper 40s for reducing our total. But having said that, it'll be the highest starting point for this fiscal year. So that's quite an achievement. Very impressive. So that's something to look forward to. If you go ahead and scroll forward a bunch to the next page, please. And this gives you the breakout of how many Night Sky Network accounts we have. That's what we pay money for. And then we have the number of FWAS members, and that's what we say when we're collectively talking about family members as well as individuals and students. So every year, or I'm sorry, every month, we list out everybody's name that's joined. And go down to the next. This area right here is showing the renewal cycle, and actually we're sitting at 49. We had, 48 non-renewals. And you can see from, you can see there from the breakout that Zelle is absolutely the #1 way that people pay. And for those of you that have used it, I want to thank you from the bottom of my heart because it is extremely easy to process based on that. In fact, a gentleman who was just here that signed up, I think it took somewhere around 45 seconds for that transaction to show up on our bank account. So, and then there's no paper. It's just wonderful. Go ahead and flow the next one. So this slide here, in the time that I've been doing this, I've never seen past 200. And now we're past 220. And unfortunately, we're going to be sitting somewhere around 170 or 160, between 160 and 170. But that's a lot better than the cliff bottom that you see from last year. And if we were to go back and look at the June 2023 Treasurer's report, you would see it's even lower than that. And the prior year to that was even lower than that one. So I think the cliff this year is going to be a small jump in a shallow water. So, are there any questions? Super, that's what I like.
Again, thank you very much, John, for your hard work and everything you do for the club. Legal Beagle, or Legal Beagles plural, any? Okay, I like that. And nothing infrastructure-wise other than the internet's going to be hooked up tomorrow. And quickly on other business.
Bring the slides up.
I'm sorry.
Can we bring the slides up? Because there's things.
Oh, okay. Financial report.
Yeah, go ahead.
Oh.
It's just an announcement of next month's presenter, K-Stars, and our understanding of them as hosts of Habitable Planets. This is work that Dr. Tyler Ricciello is doing. So I just wanted to remind everybody about next week's presentation. Go ahead.
Thanks. And thanks, Bill. Again, I don't know how
Thanks.
Bill is pulling these folks in to come pitch to us, but it's awesome, the speakers he's gotten. So table rumble, Bill. Lastly, that's not the last thing. Let's talk about the ribbon cutting on the 29th. I think the club will bring, we'll have Grandpa's Outhouse do his thing and have some water and refreshments and maybe some snacks out there. Someone mentioned something about a barbecue pit. I think potluck is probably the best thing to do. So I really hope y'all that, yes, Matt?
Do we have do we have some idea when that will start, like late afternoon or?
Not sure. You're probably.
Well, the only
around
thing I'm worried about is I'm tied up that morning.
Oh, it won't be in the morning. No.
Okay. All right, thank you.
Yeah. Probably, I'm going to guess around 6 or 6:30. And because I think the Chamber of Commerce will do something about 7:30, and it's going to dark about 8:39. So something along those lines. We'll get it firmed up and get an email out by the end of the week. So does that sound like a plan? Okay. Well, really, again, hope you guys can make it out there. It's a short 2-hour drive from here, and it's well worth it, especially now for all the work that everybody's done. Okay, questions from the Zoom world? Next slide, please. Refreshment. Okay, the social house for some socializing for those that are interested. It's not too far from here. And at this point in time, I'll make a motion to close the meeting. All in favor? Thanks. Again, thank you everybody for allowing me to help this club. I've enjoyed the 2 years. Thank you.